Hello, stargazers and the curious minds, and welcome to this channel. When we look up at the night sky, we see countless stars, such as you know, uh, huge, large stars with planet. Each has a potential sum of a alien world, and when we gaze at images from powerful telescopes, we behold galaxies, vast islands of stars, gas, and dust. But what if I told you that the age of the galaxy profoundly dictates what kind of planets can form within it? What if the universe literally had a recipe for planets and the recipe changed dramatically over billions of years? It's a mind bending concept, isn't it? We often think of planets' formation as a relatively uniform process. Stars are born from a disk of material which forms around them, and the planet, kind of freeze into the spherical shapes. And largely that's true on a local scale. But zoom out to the galactical scale and over the cosmic time scales, the rules of the game changes. The early universe was very different place, and the galaxies that formed back then were vastly different from the ones we see today. These differences, subtle at first glance, have had monumental implications for the type of planets orbiting their stars. To understand this, we need to talk about the cosmic recipe. When the universe began with the Big Bang about 13.8 billion years ago, it was incredibly simple. The only element that existed in significant amounts were hydrogen and helium. These two lightest elements made up to 99% of all normal matter. Everything else, things like carbon, oxygen, iron, silicon, calcium, all the elements that make up you and me, our planet Earth, were virtually non-existent. Astronomers have special terms for everything heavier than hydrogen and helium. They call them metals. So the early universe was, to put it in simple terms, was metal poor. So where did all these crucial metals come from? The answer ironically lies within the very object that formed the planets, which are stars. Stars are incredibly, huge cosmic furnaces. These nuclear fusion in their core, they take lighter elements like hydrogen and helium and fuse them into heavier ones like carbon, oxygen, nitrogen, and even up to iron. But the real firework happens at the end of the massive star's life. When these stellar giants exhaust their fuel, they explode in spectacular supernovae. These explosions are so powerful that they create even heavier elements, scattering them across the galaxy. This process of star creating heavier elements and then scattering them into the interstellar medium is called the galactical chemical evolution. Each generation of stars enrich the galaxy with more and more metals. Think of it like a cosmic feedback loop. Old stars create metals, and new stars form, from metal enriched gases. These new stars create even more metals, and so on and so forth. Over billions of years, the chemical composition of the galaxy slowly but surely changes. Now, let's tie this back to planets. How do planets form? They emerge from vast disk of gas and dust that surrounds a newborn star. In this swirling disk, tiny dust grains collide, sticking to each other and gradually grow into pebbles, then rocks, then small planets, and eventually full-size planet. But what are these dust grains made of? Well, they are made of these metals. We just talked about them: silicon, iron, magnesium, oxygen, and their compounds, carbon compounds, essentially the stuff that makes up the rocky material. Here is the crucial part. You can't make a rocky planet like Earth out of just hydrogen and helium. Hydrogen and helium are gases. To build solid rocky worlds, you need solid building blocks. You need metals. So the galaxy that is metal poor simply doesn't have enough of the raw ingredients for easily form rocky planets. Conversely, a metal-rich galaxy has abundance of these heavy elements, making rocky planets formation much more efficient. Let's rewind to the early universe. Just a few billion years after the Big Bang, the first galaxies were just simply forming. These were typically smaller, more chaotic, and most importantly, very metal poor. The stars forming in them were often massive, hot, and blue, burning through their fuel quickly. With such scarcity of heavy elements, the chances of forming Earth like planet were slim to none. So, what kind of planet could form? Mostly gas giants. These massive worlds are primarily made of hydrogen and helium and abundant, because those were the abundant elements. They didn't require much in a way of metals to form their bulk. Some theories suggest that the metal poor environment, the small amount of rocky material that did exist, might have struggled to form quickly enough, allowing gas to be accreted on the nascent core much faster, leading to a prevalence of gas giant. Perhaps even super Earth that were mostly icy rather than truly rocky. It's a universe where hot Jupiters might have been the norm and rocky planets were rare jewels. Let's bring this closer to home, our own Milky Way galaxy. Milky Way isn't uniform in its metallicity. The central bulge, the oldest part of the galaxy, tends to be more metal poor. Though it's complex, the thin disk where our solar system resides is relatively metal rich, especially the inner regions and the halo. The oldest and the most diffuse part of the galaxy is extremely metal poor. Astronomers even classify stars by their population based on their metallicity. Population 3 stars are purely theoretical. The very first stars formed only from hydrogen and helium. We haven't directly observed them, but they are crucial to the story. Population 2 stars are older, metal poor stars, often found in globular clusters and the galactic halos. These stars formed when the galaxies were much younger and less enriched. Planets around these worlds likely be gas rich. Population 1 star are younger, metal rich stars like our own Sun found in the galactical disk. These are the stars most likely to host rocky planets. Our Sun is a population 1 star formed about 4.6 billion years ago when the Milky Way had accumulated a healthy supply of metals. The fact that our solar system, with its abundance of rocky planets, including Earth, formed around a population 1 star in metal-rich part of the galaxy is no coincidence. It suggests that there is a kind of Goldilocks zone for rocky planet formation, not just in terms of distance from star, but in terms of galactical environment and its age. So younger metal-rich galaxies are prime real estate for rocky planets, but what happens as galaxy age further? Billions of years passes, gas and dust are either used up in star formation or ejected from the galaxy. Star formation slows down dramatically. Old massive stars have already enriched the galaxy, but the new stars aren't forming at the same rate. This leads to a different problem. In a very old, especially elliptical galaxy, star formation has mostly ceased off. The gas and dust clouds, the raw material for new stars and planets, are largely gone. While these galaxies might be highly enriched with metals from past generations of stars, there is simply not enough new star formation occurring to create new planetary system. The planet factory has effectively shut down. Existing planets would be ancient, but new ones are rare. Interestingly, when we look at the exoplanet discoveries, we find wide variety of worlds: super Earth, mini Neptunes, and these are very common. Super Earths are rocky planets, larger than Earth but smaller than Neptune. Mini Neptunes are gaseous planets, again larger than Earth but smaller than Neptune, with thick atmosphere. The prevalence of these type of planet tells us something about the common processes of planet formation in different galactical environment at different times. It is not just the overall galactical metallicity, but also the type of stars that form. In metal poor environment, the conditions might favor the formation of more massive stars or perhaps different distribution of stellar types. Our sun is a G-type star. Many exoplanets are found orbiting M dwarfs, smaller and cooler stars. The distribution of these stellar type can also be influenced by the galactical age and metallicity, which then further impact the type of planets that can form around them. So, what does this mean for the search for life? If the rocky planets are essential for life as we know it, then the early universe with the metal poor galaxies were likely a much lonelier place. The conditions were abundant rocky planets formation, and thus the potential for life probably didn't become a widespread phenomena until several billion years after the Big Bang, when galaxies had enriched themselves with enough heavy elements. This concept also ties into the galactical habitable zones. Just as there is a habitable zone around a star, some scientists propose there is a habitable zone within the galaxy itself. Too close to the galactical center and the intense radiation and frequent supernovae might make life difficult. Too far and the metallicity might be too low to form rocky planets. Our solar system sits in the sweet spot, not too close, not too far, and in the metal-rich region that allowed Earth to form. As galaxies continue to age, their stars forming gas and dust will eventually be depleted. While metals will still be abundant, the opportunity to form new stars and planetary system will dwindle. The universe is finite, and even the planetary factory has a lifespan. We might be living in a peak era of rocky planet formation in many galaxies. This understanding reframes our perception of Earth. It is not just that we are a rocky planet in we have a rocky planet in a habitable zone around a stable star. We are also the product of the galaxy that had matured enough, had accumulated enough heavy elements to provide the perfect ingredient for our world. Our existence is deeply intertwined with evolutionary history of the Milky Way itself. So the next time you gaze at a distant galaxy, remember it is not just a collection of stars, it's a cosmic canvas whose age and chemical history have shaped the very fabric of its planetary systems. From the metal poor gas giant rich early universe to the metal rich rocky planets bearing galaxies of today, the story of planet formation is a story of cosmic evolution. It's a testament to the incredible dynamic processes that have unfolded over billions of years, leading to the diverse and wonderful worlds we are only just beginning to discover. I hope you enjoyed this journey through galactical time frame. What did you find most surprising about how a galaxy age shapes its planet? Let me know in the comments below. And if you're fascinated by the universe and want to explore more cosmic mysteries, please like this video, share it with friends, and subscribe to our channel for more astronomical adventure. See you in the next one.